In this video, we'll talk about how we can look at the derivative not just about a single point, but as a function for any value of x. An important fact about the limit we use for the derivative is that we can do the same value for any x. So we don't have to just find this limit at 1. And if we wanted it at 2, find it separately at 2. What we can really do is combine all of these together and just find it for some input value of x, and then plug in our x later on. And so when we're doing this, we're defining a new function that will give me the slope of the tangent line at each point. Right, this function does what you would do normally, right? I want the value now at 3. So what do? Well, I write limit h equals 0, f of 3 plus h minus f of 3 all over h, simplify it out and solve it. But if there's a way we can simplify this formula for an arbitrary x into a nicer formula, we can get an easier way to do this process. We can define this function and then just plug in the values we want. And this is the way we more commonly refer to the derivative. So for a function f, the derivative is a new function, usually written f prime of x in one set of notations, which, for any value of x, gives me the slope of the tangent line to the graph of f of x at that point. So given this function, I could find the tangent line slope at 1, at 2, at 3, just by plugging numbers into this f prime function, as opposed to having to do the limits from scratch. This function is computed by the limit we had before. F prime at x is defined to be the limit as h goes to 0, f of x plus h minus f of x all over h, if this limit exists. Now, if this limit exists at a point a, we say this function f is differentiable at a. This basically means the function has a derivative at this point. And then finally, a function is differentiable on an interval if it is differentiable at every point in that interval. So that's our basic idea of what we mean for a function to be differentiable and to find the derivative of a function. So notational here, there's two main types of notation that are used for finding derivatives, based on the two different people who sort of developed the initial round of calculus, Newton and Leibniz. Newton is normal Isaac Newton. Leibniz is another German mathematician who sort of independently developed the same ideas that Newton came up with, but had a different notation for them. So for Newton's notation, that's what I wrote in the last page. This is using f of x for the function, and you use f prime of x for its derivative. For Leibniz notation, you will use f of x for the function again, but for the derivative, you write this as df dx or ddx of f. So Newton's notation is generally simpler because it's just a prime to tell you what's going on, but Leibniz gives you more information. Sort of critically here, it tells you explicitly what the variable is you're taking the derivative with respect to. This becomes really important with applied problems later on, when maybe you want x, maybe you want t, maybe you want different sorts of things. Leibniz notation is more explicit in what you're differentiating with respect to, and not just the function that you're differentiating. It's also used if you get on taking Calc 3, where there are now multiple variables in your problems. You have to deal with which one you're differentiating and which one you're not. So as an example here, I want to find the derivative of the function f of x equals x squared. All we have at this point is our standard definition. So let's just work that out from the definition. But instead of putting a number at the start, we're just going to put in x and solve for it as a function of x to see what we get at the end of the day. So we find the function f prime of x by writing the limit as h goes to 0, f of x plus h minus f of x all over h. We can now plug in our function f here. So I get the limit as h goes to 0 of x plus h squared minus x squared over h. I can expand out that binomial there to get x squared plus 2xh plus h squared minus x squared over h. The x squareds will cancel, leaving me with limit h goes to 0, 2xh plus h squared over h. Now I can cancel an h from every term to leave me with limit as h goes to 0 of 2x plus h, which is 2x because the h goes to 0 when I hit the limit there. So my end result here is that for the function f of x equals x squared, f prime of x equals 2x. And so if I wanted the slope of the tangent line at 4, I can now just plug in 4 and get the slope as 8. If I want it now at -5, I plug in -5 and get the slope as -10. Once I have this function, I can more easily figure out what the slopes of tangent lines are. Now I can just plug in numbers to this f prime instead of working derivative start to finish every time. That's the idea of taking the derivative as a function and then being able to use that function to find slopes of tangent lines and other information you need about this function later on.